All right, so what we're going to be talking about today is Stokes Theorem. And Stokes Theorem is a lot like Green's theorem, and it's a lot like the divergence theorem later on, in that essentially what we're doing is we're taking the fundamental theorem of calculus and we're generalizing it to some other situations and also to higher dimensions. So the fundamental theorem of calculus, when we saw it, was a single derivative, a single integral. We related our derivative to the integral, right? Okay, basically that if we knew that we had a function f and its any derivative was what we call big F, then we could take the integral of f on from a to b, and that would just be big F of b minus big F of a, right? We'd only have to figure it out on the endpoints. And so essentially that's kind of what we're doing here. But in this case, what we're doing is we're finding the value of the line integral f dot dr and comparing that to the curl of f. And so you can kind of think about the curl of f as being like the derivative, okay? So let's just recite what Stokes' theorem actually is. So we're going to let S be a piecewise smooth oriented surface with a boundary that is a simple closed curve C with a positive orientation. All right. Essentially, when we talk positive orientation, we're talking about like if you were to be moving around the surface, you'd always have the surface on your left-hand side, and that would be your positive orientation for the surface. If f is a vector field with component functions that have continuous partial derivatives on an open region containing S, then the line integral of f dot dr is going to equal the double integral over the surface of curl of f dot ds, or basically the surface integral of curl of f dot ds. Why are we going to use this? We're going to use this when it's actually easier for us to, say, for example, go find the surface integral than to find, say, for example, f dot dr. You can see these things happening quite a lot. I mean, say, for example, if we have linear functions for f, if f is a bunch of linear functions, or if f, if you look at f and you see, oh, you know, if I took the partials with respect to, you know, x and y and z, I might actually simplify my integral quite significantly. And that really is going to help us out as we go through and calculate integral. So let's use Stokes' theorem now to calculate the line integral of f dot dr, where f equals, and we got xy, x squared plus y squared plus z squared, yz, and c is the boundary of the parallelogram with vertices 0, 0, 1, 0, 1, 0, 2, 0, negative 1, and 2, 1, negative 2. So a couple things to note here. One is that this line integral, while not incredibly difficult, is actually really kind of time consuming because what we have here is we have a parallelogram with 4 sides. So to calculate this line integral, we're actually going to have to calculate 4 separate integrals. And that could take us a while. Okay, we'd have to go through, parameterize each side, then go out and actually find the value for the line integral along each one of those sides, add them all together, that gives you your line integral. Well, that's not actually really all that efficient, and not only that, there probably are easier ways to go about doing it. Not only that, when I look at f, I've got xy, x squared plus y squared plus z squared, and I've got yz. And if I kind of think to myself, when I take the derivatives of those functions, they're going to simplify quite significantly. Okay, so or the partials, excuse me. So my curl might be actually something pretty simple. All right, so I might actually have a pretty simple curl. So what I'm going to do is I'm going to use Stokes, and I'm going to let this equal then the double integral around the surface of the curl of f dot ds. So I'm going to use Stokes's in order to actually find this line integral. So what I'm going to do first is I'm actually going to go in and I'm going to draw a picture of what this might look like. Okay, I got to kind of think it through a little bit to help myself out because I've also got to go through and parameterize the surface. So I've got 0, 0, 1. Okay, so let's say that that's 0, 0, 1. I got 0, 1, 0. 0, 1, 0, there's that. 2, 0, negative 1. 2, 2, 0, negative 1. Okay, and 2, 1, negative 2. So 2, 1, and then negative 2. Okay, so I kind of imagine that I've got this parallelogram in space. It's essentially a plane. Okay, probably could have made a better one, I guess, but there we go. And so what we want to do is we want to actually find the equation for the surface. So what I did here was I went out and I found the equation for the plane, just basically took 2 of the vectors. Be careful, because 2 of the vectors are parallel to one another. So I took 2 of the vectors, found the cross product, got the normal, and then went out and found the equation for the plane. Okay, so now that I have the equation for the plane, I also need the values for my x's and my y's. So we'll notice that my y's are going to range from 0 to 1. So we start at 0, end at 1. So y is going to be greater than or equal to 0 and less than or equal to 1. And my x's are going to go from 0 to 2, right? So x goes greater than or equal to 0, less than or equal to 2. Cool, cool. Now, let's go out and let's calculate the curl. Okay, so we'll calculate the curl. I've got I, I've got j, I've got k. I've got del x, del y, del z, xy, x squared plus y squared plus z squared, and yz. And so what I'll get now is I've got z minus 2z, I minus 0 minus 0 j plus, and this will be 2x minus x k. And so that ends up equaling negative zi minus plus 0j plus xk. And there's our curl. What should be apparent here is how simple that's going to be to actually go out and find the dot product when we dot it with dot ds. Okay, we've got negative zi plus 0j plus xk. That's going to be really, like, it's going to end up being very clean when we actually go in to integrate. Let's go in now and let's calculate ds. So remember, ds is going to end up, we're going to need tu cross, or tx in this case, cross ty. Those are our parameters, and then it'll be just dy dx. Our parametrization, if you remember, is x, y, and then we've got z as being 1 minus x minus y. So tx, and again, like I said, sometimes this gets really easy, is 1, 0, negative 1. And ty is going to end up equaling 0, 1, negative 1. Take the cross product of those two, j and k, 1, 0, negative 1, 0, 1, negative 1. And we end up getting 1i plus, or rather minus, always, minus negative 1j plus, and then 1k. All right, and so that's actually equal to 1, 1, 1. So we've got negative z 0x, right, is our curl. 1, 1, 1. That's ds, so that should be pretty easy to work with. We just need to now plug in our parametrization into here. Okay, so that's going to be negative z. So we're going to get the integral, or the double integral. We're going to go our y value 0 to 1, our x value 0 to 2. We're going to have z 0x dotted with 1, 1, 1, dy dx. Z is equal to, okay, so now double integral 0 to 2, 0 to 1. And our z is going to end up being equal to 1 minus x minus y. Oh, pardon me, this is negative z. Excuse me, negative z is going to be negative 1 minus x minus y, comma 0, and then x. And then again, dotted with 1, 1, 1. dy dx. This will then equal the integral from 0 to 2, 0 to 1, and this is now going to be negative 1 plus x plus y plus 0 plus x dy dx. So that equals the integral from 0 to 2, 0 to 1, negative 1 plus 2x plus y dy dx, which is pretty, is not tough to integrate even as a double integral. So we'll go out, we'll find it. We get negative y plus 2xy plus y squared over 2, evaluated from 0 to 1. And we'll integrate that from 0 to 2 dx. This ends up giving me negative 1 plus 2 plus 1/2. I got that 0 integrated from 0 to 2. And that's 2x, excuse me, dx, which is the integral from 0 to 2 of negative 1/2 plus 2x dx, which is just 0 to 2, and, excuse me, which will be just negative 1/2 x plus x squared, evaluated from 0 to 2. This is just going to then equal negative 1 plus 4, which equals 3. And that's the value for our integral. What you will notice here, right, we didn't have to go through and parameterize 3 times. I know it seemed like it was a lot, but that's just because there's a lot of explanation here. Really, going through and using Stokes Theorem here simplified things quite significantly. All we really had to do, right, was we just had to figure out what the surface was, how to create the parameterization for the surface, and that made things a lot easier, okay, to go out and calculate the value for the line integral. You can go in and you can actually go calculate that line integral, and you'll see it's 3. I did it. It was no fun. Okay, so essentially that's going to be one of the things that we take a look at. If it goes in and like actually finding the curl gives you a much cleaner integral to work with, you probably want to consider using Stokes. All right, so let's take a look at another example. What we want to do now is we're going to look to evaluate the curl of f dot nds over a surface, and we've got this. The vector field is xyi plus x squared j plus z squared k, and c is the paraboloid z equals x squared plus y squared, and the plane z equals y, and we're going to use the outward normal vector. Now, what we're going to do using Stokes Theorem is we're actually going to then calculate the line integral around c of f dot dr, okay? And the reason why we're going to do that is because actually what this will allow us to do is it'll allow us to just calculate this line integral around a fairly simple curve. Okay, a fairly simple curve, and that's the intersection of the plane z equals y and z equals x squared plus y squared. Okay, so what we're going to do is we're going to imagine that we're going to actually kind of create, we're going to, essentially create a plane, all right, and this plane, let me show you a picture of it. The plane is going to be the intersection between that paraboloid and this plane z equals y. All right, what you're going to notice is that it's just a circle, okay? It's just a circle. It's a circle that's going to end up having a radius of 1, and if we actually map it down onto the xy plane, what you'd see is that it's the circle of radius 1, and it's got a its center is at 0, 1. Okay, so it's got a center at 0, 1, and it's got a circle of radius 1. All right, and so that's going to be fairly easy to create, kind of basically to create a parameterization of that line, and then go find the line integral of f dot dr, rather than going out parameterizing the surface, okay, and then going find curl of f dot ds. Okay, so that's kind of the idea that we're working with there. So I think one of the easiest ways to go about doing this is or to see that actually is going to end up being the parameterization, is I'm going to let z equal, I've got z equals r squared, x squared plus y squared, so I'm going to actually rewrite that in polar. So z equals r squared, and then I'm going to have that z equals r sine theta. Okay, so z, r squared is going to equal r sine theta, and so r is going to end up equaling just sine theta when we just divide through by r. Okay, so I get r equals sine theta, and if I were to draw that out, okay, what I get, as I said before, is I essentially get a circle, right? But instead of being centered at the origin, right, it's essentially a unit circle, but instead of being centered at the origin, it's centered at 0, 1. Okay, so the parameterization that I'm going to use for this is I'm going to use, I'm going to rewrite this. I'm going to have it be x squared plus y minus 1 squared equals 1. And so that's going to be then cosine t is going to equal x, and then I'm going to have y minus 1 equals sine t. So y is going to equal sine t plus 1. And then because z equals y is my plane, and I'm concerned with the figure on the plane, I'm going to let z equal sine t plus 1 as well. So my r is going to end up equaling cosine t, sine t plus 1, sine t plus 1. Okay? And then I can go in and I can rewrite f in terms of r. So f of r of t is going to then equal, and this will be cosine t times sine t plus 1 plus cosine squared t. Excuse me, not plus, but we'll just use commas. And comma, and then sine t plus 1 squared. So now I'll take r prime of t, and that's going to end up equaling, is going to equal negative sine t, cosine t, cosine t. So now we're going to dot those two together. So I'm going to dot, I've got f of r of t dotted with r prime of t. And that's going to equal, right, cosine t, sine t plus 1, cosine squared t, sine t plus 1 squared, dotted with negative sine t, cosine t, cosine t. This ends up equaling negative sine t, cosine t, sine t plus 1 plus cosine cubed t plus, and this will be cosine t times sine t plus 1 squared. And we actually go in and simplify that. Little simplification. I end up with cosine t plus sine t cosine t plus cosine cubed t dt. Cosine cubed t, excuse me. And so if I take my integral, the integral, our t is going to go from 0 to pi. Okay, that's because it's not actually centered at the origin. It's actually centered above the origin. So we're going to go from 0 to pi. And it'll be cosine t plus sine t cosine t plus cosine cubed t dt. And when we integrate that, this ends up equaling 0. And so what we end up getting is we end up getting 0. It does, again, it seems like a bit of work, but if you actually think about it, it's a lot easier than actually going in and parametrizing the surface, right? All we had to do was we just had to go out and calculate the line integral around that curve, the one that we saw inside of the graph, right? Which is basically this, the unit circle centered at 0, 1, but up on the plane, z equals y, okay? And so consequently, what we end up getting is we end up getting something that's actually pretty fairly simple to go in and integrate, and we end up getting it. So one of the big takeaways that we get from Stokes' theorem is that if we don't want to calculate the surface integral for the curl of a vector field, right, or if we have a surface that's actually quite difficult to parametrize, we can choose to find the line integral of the curve that encloses the surface that we're looking at. So like an example is something like this. This is kind of a bit of a made-up example, but you can see that if our surface is actually the purple thing, okay, we got this entire purple thing, we don't actually, Stokes' theorem tells me that I don't in fact need to go out and parametrize the entire purple thing. Instead, I can just go in and find the line integral around this curve right here that encloses, right, okay, that encloses the entirety of my surface, okay, which is very much, is just this circle right there. That's, basically a circle, radius 1, okay, my C is a circle, radius 1, in the xz plane, Okay. So basically surface radius 1 in the xz plane. Notice also that it is centered at the point. It's not centered actually at the origin. It in fact is instead centered at the point 0, 0, 1. Okay, so you'd actually have to change the parameterization just a little bit, but that's not too hard, right? In terms of going out and finding the parameterization for the line, okay, or for that curve. And so we just go out, we find the parameterization for the curve, and that might be a lot easier, a lot simpler to go out and calculate. Okay, and so that's one of the things that we want to actually be able to do is we want to be able to look at something and say, you know what, I'd rather go find the line integral right now rather than going out and finding, you know, this double integral or the surface integral. So now let's take a look and let's use Stokes Theorem to calculate the surface integral for this surface. You take a look at the surface and you think to yourself, well, I don't know how I would go out and parameterize that surface. And you know what, I don't know how either. But if I go in and I take a look, what I can see is that I in fact have the boundary curve, C here, is in fact fairly simple, right? It's essentially a unit circle. They're telling us r equal to 1, and it's in the xz plane. Okay, so it's essentially, it's x squared plus z squared equals 1. So that's actually the boundary curve there. And so I can let x equal cosine t, I can let y equal 0, and z equal sine t, and that's going to end up being my parameterization. So r of t now is going to end up equaling cosine t, 0, sine t. Okay, and that ends up being, you know, a pretty simple thing for us to work with. Now, all I need to do now is I need to figure out what f of r of t is. And so that ends up equaling sine t, cosine t, 0. Okay, and I want to note as well that my t is going to be less than or equal to 0, less than or equal to pi, right? 2 pi, excuse me. So I can now figure out, right, that I'm now going to take the dot product of f and r prime of t. So r prime of t is going to end up equaling negative sine t, 0 cosine t. So f dotted with r prime of t is going to end up equaling sine t, cosine t, 0, dotted with negative sine t, 0 cosine t, and that ends up equaling just negative sine squared t. So my integral, my double integral, my surface integral, the curl of f dot ds, okay, is going to end up equaling the integral from 0 to 2 pi of negative sine squared t dt. And that's not too much of a problem. We go in, we integrate that. That ends up equaling negative pi. And there we go. So you can see how much easier it is to do that than to actually go out and figure out the parameterization for that surface, if at all even possible to find the parameterization for the surface. All right, so all we need to do is actually find a boundary curve. And that's one of the great things about Stokes Theorem is that it essentially allows us to simplify problems that would be otherwise unmanageable. We wouldn't be able to do them. All right, so now what we're going to do is we're going to use Stokes Theorem, and we're going to have a boundary. We're actually going to find a line integral here using Stokes. So what that means is that we're going to actually find the surface integral of the curl dot ds, or the curl of f dot ds, rather than finding the line integral. So let's consider that we have this surface, z equals x squared plus y squared, with x greater than or equal to 0, less than or equal to 2, and y greater than or equal to 0, less than or equal to 1, oriented with an upward facing normal. And then we have our vector field f of x, y, z is going to equal sine x cubed plus xzi plus x minus yzj plus cosine z to the 4th k. So what I'm going to do, right, is I'm going to let this by Stokes. This means that I'm going to find the surface integral of the curl of f dot ds. Okay? My parameterization for my surface is actually already given. So that's kind of cool. That's good. So I'm going to let r of, it's going to be xy, we'll just choose xy, equal then x, y, and x squared plus y squared. And then our bounds are given as x is greater than or equal to 0 and less than or equal to 2, and y is greater than or equal to 0 and less than or equal to 1. Okay? So, if I find t of x, my tx is going to be 1, 0, 2x. My ty, my tangent y, is going to equal 0, 1, 2y. Then I'm going to go find the curl of f. Okay, so delta x, delta y, delta z, sine x cubed plus xz, x minus yz, and z to the cosine z to the fourth. Okay, so I go in here, start out with taking my cross product. I'm going to get 0, and then this is going to be negative y. 0 minus a negative y, excuse me. I plus, minus, and then we'll have, this is 0 minus, and then this is just going to be minus x, z, excuse me, j, plus, and then we'll get 1 and plus 0, k. So our curl actually turns out real nice, real tidy. So this is going to end up giving me yi plus xj plus k, or yxk. Great. And now I'm just going to find the dot product of the two of those, because we want the curl of f dot ds. So I've got yxk dotted with, first I have to go find that cross product. I need the cross product tx cross ty. So that's going to be 1, 0, 2x, 0, 1, 2y. This ends up giving me negative 2xi plus, or minus, excuse me, minus j, excuse me, minus 2yj plus k, or negative 2x, negative 2y, and 1. Now I'm going to dot them. I actually changed this to a k, from a k to a 1. I said 1, then wrote k. So this is going to then be negative 2x, excuse me, do the other way around, yx1 dotted with negative 2x, negative 2y, 1. And this then equals negative 2xy minus 2xy plus 1, which equals negative 4xy plus 1. Now, since we are using, we're finding the line integral, we're going to use the double integral. And remember, our bounds are going to be from 0 to 1. We'll start with y, and then 0 to 2. And this will be then negative 4xy plus 1 dy dx. That'll then be negative 4 xy squared over 2 plus y, evaluated from 0 to 1. And then we'll evaluate that 0 to 2 dx. This is then going to equal, okay, negative 4, or excuse me, negative 2x plus 1. We'll evaluate that from 0 to 2 dx. And that'll then equal negative x squared plus x evaluated from 0 to 2. That equals negative 4 plus 2, which equals negative 2. And that ends up being the value for our line integral. A couple things to notice about this here. One, we were given the parameterization of the surface, so that actually made things like really very easy. That's probably one of the harder parts to do here. But two, notice that this is kind of gnarly in terms of, you know, sine x cubed plus xz, x minus yz, and cosine z to the fourth. But also notice, like, this cosine z to the fourth, that's in the z. It's like the z component. And so consequently, we're never actually going to take the derivative with respect to z of it, right? See how it ended up inside of the curl? We never took that derivative with respect to z, so it went away. It zeroed out. And same thing over here, sine x cubed, that's in the x component, so we're actually going to zero that out pretty much too. So consequently, what we ended up with was we ended up with a curl that was pretty neat, pretty tidy. So what should be apparent here is that Stokes' theorem allows us to choose the path of least resistance when we're going through and integrating, making things a lot simpler. Allowing us to, if we have a fairly simple parametrization of a surface, then use the surface parametrization. If, on the other hand, the curve is, or the curve that encloses the surface is a lot easier to use, go ahead and use the line integral, right? If you end up having a really tidy curl, like when you go out and you find the curl and it ends up like zeroing everything out, go ahead and use that, okay? If you've got a conservative vector field, heck fire, go ahead and use that too, because, well, what you'll get is obviously this is going to zero everything out. That's going to make things a lot easier. So basically the idea here behind Stokes' theorem is that we are going to select either we're going to utilize the surface integral, okay, or we're going to use the line integral depending upon which one is easiest for us to use, okay? And it just turns into one of those really great things that we can do in mathematics that like makes life more elegant.